Hi everyone and welcome back. Today we are looking at multiple linear regression. So this is a little bit different to what we did last week. So last week we looked at simple linear regression where we took a single DV and we regressed it onto a single IV. This week instead of that we're going to be taking that single DV and regressing it on 3 IVs all at once. And this is going to give us some very interesting and some interesting results that are a little bit different. So rather than, like last week, looking at each one individually, talking about its R-squared, what we're going to now do is layer everything on top of each other. And this is going to effectively partial out any overlapping variance between our 3 variables. So I guess if I was to try and show this visually, what we did last week, I spoke about the R-squared being the variance explained in the dV by the IV. The other way that I worded it is how many of the reasons why a person got the score they did on their DV can be explained by the IV. So if you imagine for a second that this circle contains all the reasons why a person got the score they did on their DV. So it's including reasons like the person who took cocaine when they were making their project and were able to stay up till stupid o'clock in the morning. But it also includes people like the person who didn't stay up late and only spent a couple of hours. And then I have another circle that represents the number of hours put into research. Actually, I'm just going to call it IV. And this is the variable that we were really interested in last week. It's the one that I spent the most time explaining. Now, that R-squared that we got for the relationship between the judge's score and research effectively is the overlap between these two circles. It's the amount of variance explained in the DV by the IV. What proportion of the reasons why a person got the score they did on their DV can be explained by the number of hours of research they put in. Now that same concept still holds in multiple regression, but the difference is now that we have other variables as well. So let's say our blue circle represents the number of hours you put in for research, and then the red circle is how how innovative your project is. And we know from last week that these were the two biggest predictors. Now, there is a possibility that there's some overlap between those two variables. That, in other words, the level of innovativeness of your project might have some relationship with the number of hours of research you put into the project. So when you do a multiple regression, that overlap actually gets removed. And instead, what you're actually analyzing, and what our R-squared's now going to represent, is just the unique sections, the unique variance explained by each IV. So we will now get, we won't get an R-squared for each IV, we can get a different metric for that if we're interested. But when we start looking at our betas and our t's and our confidence intervals, it's going to be on these unique sections. So the section, in this case, for the number of hours spent being built, so our red circle, how many of the reasons in our DV, in the judge's score, is uniquely due just to how innovative the project is. And then for our number of hours spent researching, it's the same thing. So we are removing this overlapped area here, which are the reasons why a person got the score they did, because of the overlap between the innovation and the number of hours spent researching. So we're removing the overlap and we're just looking at these unique chunks. I know that's a really, really abstract concept, but if you can understand that at this sort of abstract level, that's as far as you need to take it. Once we start looking at the analyses, as long as you know that conceptually this is what's happening in the background, it'll make sense why all the numbers change when we get to this next analysis. That's really all we're trying to explain here. Okay. So we're using the same data set from last week, that's why I was using those examples. So let's make sure I've loaded that up. Okay, and we can see that our data is here. We can see some residuals that have been calculated, so let's remove those. Because we can calculate those later if we want to. So just to remind ourselves, we do now have a new research question from last week. So last week we had 3 research questions, this week we have 1. And that research question is, can we predict the judges' scores of science projects from a combination of the number of hours spent researching and building the project and the level of uniqueness or innovativeness of the project? It's the same sampling population from last week, so it's our Year 6 students. And it's the same data structure, so we haven't got any new variables. Now, bring it all together. The design is still correlational, we're not manipulating anything. The research question involves prediction, but now we're using multiple predictors simultaneously. So last week our research question involved prediction using a single predictor at a time. Now we have 3 predictors we're going to use all at once. So last week we had 3 research questions where each predictor was used in turn, and now we're using all 3 at once. So that's a really big distinction. In this case, our DV and our IVs are all numeric. So this tells me then that multiple linear regression is the most appropriate test to be using. Now, if this was the first time I was picking up this data set, I would go through my univariates and my bivariates. However, that's not appropriate for us today because we did it all last week. So we're going to skip all of that and jump straight to the regression model. Now, we do get all the stuff over and above correlation that we spoke about when we use regression. But now I want to talk a little bit more about the overall model statistics. So last week I said that this wasn't too important for simple linear regression, but would be really, really important when we get to multiple. So the overall model statistics essentially is asking the question whether or not the R-squared of our model, remembering that our model is whatever predictors we put into the regression, is the overall R-squared of that model significantly greater than the R-squared if we assume the null is true. So all it's asking is, by putting in these other predictors, do we actually significantly increase our R-squared? Do we actually explain variance in our DV? If the answer to that question is no, then why bother looking at the rest of the statistics? The model doesn't work. So to that extent, it's worth reminding us that when we say assuming the null is true, what we mean is that all participants are expected to get the DV score as the mean. So remember that the regression formula is all about predicting the DV score. So in the null model, we assume that the predicted DV score for all participants is just the mean of the actual DV. Now we are still going to get beta statistics with confidence intervals, and it's still the measure of the effect of a 1 unit increase on the IV from the DV. However, there is a slight difference. And that difference is that our 1 unit increase in our IV is now controlling for all the other IVs. So when I say controlling for the other IVs, I mean partitioning out this green stuff, partitioning out the overlap, the shared variance. So other ways that you could say controlling for all the other IVs is saying this is the unique effect of each IV on the DV. Another way is saying you're partitioning out the effect of all the other IVs, or you might also say the effect of one IV over and above all the other IVs. No matter how you want to think about it, all we're talking about when we get to our betas and all the statistics attached to them now is just the unique effect of one IV. So we're partitioning out the overlap. We still get t statistics and p-values that are interpreted the same way. Our null hypothesis, however, changes. So last week our null hypothesis was that beta 1 equals 0. Now we're saying that beta 1 equals beta 2 equals however many betas we have equals 0. So the null hypothesis for our regression is that none of our betas will have any value greater than 0. All of our betas equal 0. So what this means, technically speaking, in terms of our R-squared and our overall model statistics, if at least one of our betas is greater than 0, and greater than 0 as in 0 is not in the confidence interval, if at least one of our betas, so one of our IVs have a beta with 0 not in its confidence interval, our overall model statistic will be significant. It will pick up on that single predictor. So that's all we need. For our regression to be significant, all we need is one predictor to have a beta that is greater than 0.